This is a continuation of lesson 1-3. We're on example 2. Which set of numbers is most reasonable for each situation? Outdoor temperatures. Now, I know in Texas all we deal with are like 100, 101 degrees. But in other more normal parts of the world, they have lower temperatures. Sometimes they even have temperatures that are below zero, like negative 32 degrees. So if we take other areas of the world into account, then we know we'd have to use integers. Some people think rational numbers, but when we report the temperature, we almost never give the decimal portion of our temperature. They don't tell us it's 115.7 degrees outside because that 0.7 really doesn't matter to us. They would just say it's 116 degrees because when it's hot, it's hot. So we're really just going to use integers for outdoor temperatures since we usually don't use decimals. Now, the number of beans in a bag. So let's look back at our little chart. The number of beans in a bag, would that be natural, whole, integers, rational? Well, generally we won't have any negative numbers in there, so we can exclude integers. Whole numbers, that's a possibility, natural numbers. Now remember, natural numbers don't include zero, but the bag can be empty. So I'm thinking whole numbers for the number of beans in a bag, since we could have no beans at all. Whole numbers. Let's look at another one of those. Which set of numbers is most reasonable for the cost of a scooter? So when you think about how much a scooter costs, now it depends on the kind of scooter you're buying, but maybe it would be something like $95.99. They usually like to throw on that 99 cents. So you think you're getting a deal, but we know that's really basically $96. So adding on that decimal there, we know it can't be an integer because integers don't include decimals, neither do whole numbers or natural numbers. Therefore, it has to be a rational number. Great. Let's look at the next part of our lesson, which is to talk about counterexample. A counterexample is any example that proves a statement false. And we all love to do that. Well, I shouldn't say all of us, but a lot of us love to argue. And so that's what counterexample is. It's arguing and giving an example for why your argument is true. Using counterexamples, determine whether the statement is true or false. If it is false, give a counterexample. So let's look at this statement. All negative numbers are integers. Is that true? Are all negative numbers integers? What's an integer? It's a negative or a positive number, but remember, integers, no fractions, no decimals. So with that restriction then, I can think of a negative number that's not an integer. So I'm going to say this is false because of the counterexample, negative half. That's a negative number, negative, but it's not an integer because an integer can't have any fractions or decimals. Negative half would just be a rational number. So false, negative half is not an integer. And of course there are lots and lots of examples you could use. Instead of a negative half, you could do a negative 3/4, or you could do negative 0.3 repeating, or there are lots and lots of examples that you could use. Here are just a few. So let's look at a couple more counterexamples. Is each statement true or false? If it is false, give a counterexample, just like we just did. All whole numbers are integers. So here you have to think back to your chart. So remember, it's rational, inside is integer, and then inside that is your whole numbers, and then inside that are your natural numbers. So are all whole numbers integers? Definitely. That's why whole numbers are inside of integers. Remember, whole numbers are just numbers like 0, 1, 2, 3. I can't think of a single whole number that wouldn't also fall into the integer category, and that's because the category of whole is inside integer. That means, by definition, or by the description of the picture, that all the whole numbers have to be integers. So this is actually true. There isn't a counterexample. B, no fractions are whole numbers. So I have to think of a fraction that is a whole number. So what's a fraction that is a whole number? Well, how about a fraction like 4 halves? 4 halves is actually really just 2. So my answer then is false, or really, let me move that over, and then I've got my answer. False, 4 halves equals 2, which is a whole number. So we're just trying to prove the statement wrong. Of course, sometimes it's true, and so we just need to say it's true. An inequality. An inequality is a mathematical sentence that compares the value of two expressions using an equality symbol such as less than or greater than. So remember, this is less than, and we have greater than. We also have signs like less than or equal to, and greater than or equal to. This is less than or equal to. This is greater than or equal to. And then, of course, we have our equal sign. So as a quick example, we might say that 3/4 is greater than 1/2. Okay, let's look at example 4, ordering fractions. Write -3/4, -7/12, and -5/8 in order from least to greatest. Well, as it stands right now, I really have no idea how these fractions compare. But we have a couple of tools in our tool belt to help us figure out where these fractions lie. The first thing I want to talk about, though, is the number line. So since these are all negative numbers, we have to have a pretty good understanding of the number line. Let's say this is 0, 1, 2, 3, and so on, -1, -2, -3, and so on. Now I know all of these are somewhere between 0 and -1. So the closer they are to 0, the bigger they are because they're closer to being positive. And the further away from 0 they are, the smaller they are because they are more negative. They're further away from being positive. So negative numbers are kind of tricky because they're backwards of what we generally think. The bigger the number, the larger it is. Makes sense, right? But the bigger the negative number, the smaller it really is. So let's look at these fractions and try and order them. I have -3/4, -7/12, and -5/8. Now one tool to order them would be to make them all look the same. That is, get a common denominator. So we want to find the least common denominator for 4, 12, and 8. And the least common denominator for 4, 12, and 8 would just be 24. So I'm going to change all these fractions to have a denominator of 24. So what do I have to do with 4 to get 24? 4 times 6 is 24, so 3 times 6, or -3 times 6, that's -18. So it's still negative. We don't lose the negative. In fact, you can just write all those in right now. The fractions are still negative. 12 times 2 is 24, so 7 times 2 is 14. 8 times 3 is 24, so 5 times 3 is 15. And now we can easily see how they compare. Again, the larger the negative, the further away from 0 it is, and the further away from being positive it is, so the smaller it is. So we might write that. The larger the negative, the smaller the number. So let's order them. What's the largest negative? Our largest negative is this one right here, -18/24, which was originally -3/4. So that's my first fraction. It's the least number. We're ordering from least to greatest. It's the smallest number because it's the largest negative. Our next largest negative is -15/24, which is -5/8. So it was the next biggest negative, meaning the next smallest number. And then finally, -14/24, or -7/12. So -7/12. And there we have them ordered from least to greatest. This is the biggest negative, so it's the closest to -1. This is the smallest negative, so it's the closest to 0. Let's look at one more. This one's a little easier. They were nice to us and threw in a positive number. Write 1/12, -2/3, and -5/8 in order from least to greatest again. So the first thing is, I know that this 1/12 is going to be my biggest number because it's positive. So it has to be the greatest. Obviously, any positive number is bigger than any negative number. So I know that 1/12 is going to be my greatest. But now I need to figure out between -2/3 and -5/8, which one of these is the bigger negative. Remember, the larger the negative, the smaller the number. If you only have two fractions to order, there's a really neat trick you can do, and that is to multiply the denominator to the numerator. So you go up from denominator to numerator. 8 times 2 is 16. 3 times 5 is 15. And which one has the larger number above it? 16. So that means this is the larger fraction. Therefore, it's our smallest number because it's the larger negative. Remember, we're dealing with negative numbers here. If we didn't have these negatives here, then yeah, 2/3 would be greater than 5/8. But since it's -2/3, then it's the smallest number. So we know that our smallest is -2/3, then -5/8, and finally 1/12. You can, however, do just what we just did in the last one before. You can find a common denominator, -2/3, -5/8. Their common denominator would be, 24. So change them both to 24 times 3 times 3, so it's -15, times 8 times 8, so it's -16. And you can see this is the larger negative. -2/3 is still the larger negative, and therefore it's the smallest number. So either way. Okay, let's talk about opposites now. Opposites are two numbers that are the same distance from 0 on a number line, but lie in opposite directions. So for instance, the number 2 and -2 would be opposites because they are the same distance from 0. This is 1, 2 away, and this is 1, 2 away, but they lie in opposite directions. So there's an example of 2 and -2. Also 3 and -3, or 4 and -4, all of those are opposites. Absolute value. Absolute value is the distance from 0 on a number line of any given number. So for instance, the absolute value of -3 would be 1, 2, 3. It's 3 away from 0. The absolute value of 2 would be 1, 2. It's 2 away from 0. So again, absolute value is the distance from 0. And we denote that using bars. So we were just talking about -3 and 2, so let me give you those as examples. The absolute value of -3, so it's these straight bars, the absolute value of -3 is 3. It was 3 away from 0. And the absolute value of 2 is 2 because it was 2 away from 0. Last example, finding absolute value. Find each absolute value. What is the absolute value of -2 and 5/10? Well, again, it's just the distance from 0, so it would be 2 and 5/10 away. The absolute value of 7 is simply 7. It's 7 away from 0. So hopefully by now you've noticed that when you find the absolute value, it's just always going to be positive. It's whatever your number is inside absolute value, the positive version. Absolute value you can think of as like magical bars that make everything positive. Okay, let's look at a few more and then we'll be done with 1, 3. The absolute value of 5. Well, 5 is 5 away from 0. The absolute value of -4. -4 is 4 spaces away from 0. The absolute value of -3 and 7/10, it's 3 and 7/10 away from 0. And finally, the absolute value of 5/7 is 5/7 away from 0. See how easy that is? And now you can do it on your own.